Hello everyone, welcome back to the channel. I hope you guys are doing amazing. So let's dive into today's daily challenge on Leetcode and try to see the approach. So you have this question of maximum candies you can get from boxes. You have n boxes labeled from 0 to n minus 1. You are given 4 arrays: status, candies, keys, and content boxes. Status I denotes 1 if the ith box is open and 0 if it is closed. The candies I denotes the number of candies in the ith box. Keys I denotes the list of keys of the labels of the boxes which you can find inside the ith box, and content box I is a list of boxes you find inside the ith box. So these are 2D arrays. As you can see here, you are given an integer array initial number of boxes which contains the labels of the boxes that you have initially. So what you can do, you can take all the keys candies in any open box and use the keys inside it and open new boxes. You can also use the boxes you find in it and return the maximum number of candies you can get following the rules above. So let's try to understand what this means using this example. So you can see n equals to 4. We have 4 box. This means that box 0 is open, box 1 is closed, box 2 is open, box 3 is closed. And this candies means these are the number of candies present in the boxes. The keys represent that inside box 0 you find no keys, inside box 1 you find no keys, inside box 2 you find the key to box 1, and so on for others. And content boxes mean inside box 0 you find the box 1 and 2, inside box 1 you find the box 3. So, and the initial boxes you have, initial level of boxes you have only one box, that is 0. So you can initially be given 0 boxes and you will find 7 candies inside it, and box 1 and 2. Box 1 is closed and you do not have a key for it, so you will open box 2 naturally. You will find 4 candies inside this box 2 as it's open, and you will also find the key to box 1. Okay, as you find the key to box 1, now you can open box 1 also. So initially you had box 0 which is already opened, so you get 7 candies, you get 4 candies, then you get 5 candies, and then the last box will remain open because you do not have the key to it anyways. Okay, so the number of candies collected is 7, 4 and 5, it is 16. So, and you see the n is given to be 1000. Okay, and it is also told that each box is contained inside one box at most. It means that there are no duplicates. Okay, so so looking at this problem, if you see this contained box, if you try to read this line carefully, contained box is a list of boxes you found inside the ith box, and it is a key I is a list of labels you can open after opening the ith box. So what do you think? The ith box, doesn't this give the hint of an adjacency list of a graph? If you read this sentence carefully, this contained box sentence, it is a list of boxes you find inside the ith box. So that is what happens in an adjacency list, right? In if you have a graph and you have a node I, you get all the neighbor nodes that you can travel from I to the adjacency list, right? In the adjacency list in the graph. So what you can do, you can simply do a BFS here. You can simply go for a BFS. So how to do that, how to exactly do the BFS is quite simple. Also, you have, let's say you have this box, let's say 0 initially with you. So you may be given multiple boxes. So you do BFS from multiple sources. Let's say you have these boxes 0 and 3 given with you. Okay, and this is the status. You have the status array already ready, given by 0, 1, something like this. And you also have the you make another array has key, which denotes that whether you have the key or not. So what you do, as you see here, when you go to 0, you go to contained boxes to find which are the boxes which are neighbor to this, and also you go to 3 to find the neighbor boxes in here. And whenever you get the neighbor, as you do in BFS, you go to the neighbor, see the boxes which are there in it, push those boxes in the queue again. You maintain a queue in BFS, right? So if you don't know BFS already, please try to understand and then come to the video. You use a queue in the BFS, and you push all the elements in the queue, And you also mark this has key of I, has key of the box, whatever you obtain this box, you mark that one. Okay. If you can open that, mark that one. If you cannot open that box, if you cannot open the box, you just push the box number again in the queue. So what do I mean? If you have boxes, let's say 0, 1, 2, 3, 4. Let's say initially you push 0 and 3 in the queue, then you are processing this element. You see that this box I cannot open. So you push it again back in the queue. So you can do it that way. Okay. This is the only change in the BFS that you need to do. So let's try to code it and we will also understand it simultaneously. So we have the status, which will give us the status of the boxes. Okay. Also now you have this vector int has key. As I told you, I will have a vector int has key, which will, it if it is 0 means that we have the key or not. Okay, whether we have the key or not. And what we need to do now is we are going to perform a BFS. Now multiple sources will be in this BFS. That is, I will start my starting vertex at multiple points. Okay, so that is given by the initial boxes. So I will traverse to the list of initial boxes. Initial boxes dot size I plus plus. I will go through them. I will do q dot push initial boxes of I. Okay, so I pushed all elements of the queue inside the initial boxes, and that's all. I have it. So I do simple BFS now. While not queue is not empty, what do? I get the queue. Okay, I get the element, I get the box from the queue by doing q dot front, and I also do q dot pop. Okay, and now what we do in normal BFS is that we go through all the boxes, all the adjacent boxes. But if you see, you can go through the boxes only if you can open the current box, right? Only if you can open the current box. So you need to check if I can open this box. How you can open this box? Number one, if the status of box is already open, then you have nothing to do. You can all easily open that. Else, if you have the key to this box, you have the key to this box, then you can also open it, right? It's really simple. So now you have the key to the box, you have the state box already open, so you get it. Now what you need to do is, as you have opened this box, you store the number of candies count. You just add the number of candies count, right? Count plus equal to candies of box. Okay, and you can also do like you can just covers to the boxes as you do in the adjacency list, right? Contained boxes. You go through the contained box of this box. So adjacent to this box, which are the boxes, I am just pushing them in the queue. Okay. In order to process it, I have pushed it. And also I can find the keys. So I go through the keys of box, keys which I found in the box. I go through all the key, and since I have the key now, I mark that I have the key K to be 1. Okay, I just mark it. Now you have all those. Else, if what will happen if you cannot open the box? You have already popped the box from the queue, but you need to process it further also, right? So you do q dot push. Q dot push the box. You again push it in the box. Okay. So if you do this and return count, if you do this, let's try to see what happens. Do you think it will work? Do you think it will work? I just did nothing. I just use the simple BFS. If I find the keys, I have pushed the keys. You see, we get a TLE, right? So why do we get a TLE? You see, what will happen if we do not have the key at all? Let's say, for example, in this, we do not have the key at all, right? For the key to the box 3, we do not have, and it is closed also. So it will keep on processing, it will keep on pushing this queue, pushing this again and again and again. Okay. So how many times we need to push? So we set a timer here. What we do, we set a timer. This timer is initially 0. The timer will get reset every time it finds a new element, and it just increments the timer whenever you find that this box is not openable. Okay, I increment the timer. Again, you go to another box, you find it is not openable, I increment the timer. Uh, then what you do, you see that however elements are present in the queue, all those elements I have already checked, then timer will be just incremented, right? So if I find anywhere timer is greater than this q dot size, if you find this timer is greater than this q dot size, okay, so what you can do now, you can just break it, right? So there is no need to iterate again and again and again through the loop. I have my timer with me. It will increment. So whenever you find a new key, it will just reset it to 0, because it needs to check that that key will open which of the boxes in the queue, right? So if you find a new key or you find a new boxes, anything, and one box is openable, then again you need to reset the timer to 0, because you need to check again all the elements of the queue, whichever is present in the timer. Okay, whichever is present. So you need to reset the timer, and yeah, I think you have understood this easily. It's not that much difficult at all. Let's try to run it now. Okay, we do have the accepted thing. Let's try to submit it and check if we are doing any error or not. Yeah, we do have the accepted thing, and you see we have a very good runtime complexity. We are practically solving it in ON. N is the number of, like, the number of boxes is 1,000 given, and we are processing each box once, except when the timer, when we are repeating this queue only n number of times. So whenever it exceeds the size queue, we just break it off. Okay. So that's all for this problem. It's normal VFS you need to do, and a little change in the normal VFS, that is all you need to do in this problem. Okay, so that's all for today. This is a doable hard kind of problem, I will say, but I hope your day is going to be really easy. Thank you so much.